All right, let's jump right into this explainer. We're going to unpack the unseen chemical engineering that literally keeps the plastic products all around us from catching fire. I mean, we live in a world built almost entirely on synthetic polymers, right? When you look at your fast-charging phone block or the dashboard of your car, or even that memory foam mattress you sleep on every night, you probably aren't thinking about the massive scale of invisible chemistry required to keep you safe. Today we're decoding the oceanchem 2026 Flame Retardant Application Guide, and we're exploring the fascinating microscopic armor that protects our modern, polymer-driven lives.
So how exactly do the plastics around us resist fire? It's a question we rarely ask, but man, the stakes are incredibly high for industrial buyers, material scientists, and well, all of us. Plastics are super useful, obviously, but they're largely derived from petrochemicals, which kind of means that without some highly specialized chemical additives, our homes and offices are basically filled with solid fossil fuels. If an electrical spark hits an untreated plastic, it is going up in flames. So how on earth do manufacturers meet these strict global safety standards without ruining the durability, weight, or cost of their products? Well, the answer lies in the exact science of flame retardancy. Think of it as a highly technical matchmaking process, where you literally have to pair the exact protective chemical armor with the right plastic. You can't just toss any random chemical flame retardant into a batch of plastic and call it a day. No way. It requires absolute molecular precision. And if the matchmaking is off, the consequences are pretty severe. The wrong chemical additive could totally degrade the plastic, making it brittle, prone to cracking, or worst of all, it might just fail to activate during an actual fire. The chemistry absolutely must align flawlessly with both the polymer structure and the environmental standards it's trying to meet. To make sense of all this, we'll cover 5 quick steps today. First, decoding UL94 fire ratings. Second, protecting rigid engineering plastics. Third, securing foams and flexible resins. Fourth, next-gen synergists and innovations. And finally, exploring the oceanchem production hub. Let's get right into it.
Section 1. Decoding UL94 fire ratings. This is all about establishing the global standard of safety.
Before we even look at the chemicals themselves, we really need to establish the brutal baseline that these formulations have to defeat. What's absolutely fascinating about this testing process is how straightforward yet intense it is at pushing a material to its absolute thermal limit. Just picture the tension in the testing lab. Technicians take a specimen of the engineered plastic and they apply a live flame directly to it for 10 agonizing seconds. Then they start the clock. They're measuring exactly how long it takes for the flame to extinguish on its own. And crucially, they place a delicate piece of cotton wool exactly 30 centimeters below it. Everyone is basically holding their breath to see if the melting plastic will release a molten, flaming drip that sets that cotton ablaze.
And that test perfectly illustrates the hierarchy of safety that comes from the lab. If the flame goes out in under 10 seconds and there are absolutely 0 flaming drips lighting that cotton below, bam, you've achieved a V0 rating. That is the ultimate gold standard. To put that into real-world perspective, a V0 rating means that if the internal wiring of your flat-screen TV short circuits, the plastic housing just fizzles out and dies. No big deal. But if you drop down to a V2 rating, the plastic might self-extinguish, sure, but it's going to shed flaming drips first. Drips that could land directly on your living room rug and start a literal house fire. Oceanchem's primary mission is formulating the chemistry to hit that V0 mark every single time.
Moving on to Section 2, protecting rigid engineering plastics. This is the chemical armor for hard polymers.
So for common rigid plastics like ABS, the incredibly tough stuff your computer monitor or your child's Lego bricks are made of, manufacturers typically need about a 12% dosage of a specialized brominated flame retardant called DBDPE. And for industrial nylons like PA6, which are used heavily near hot car engines, the dosage can actually go all the way up to 20%. But check out the engineering leap with polycarbonate. When it's paired with a highly specialized halogen-free fluorine sulfonate, the required protective dosage plummets from 12% down to an incredibly efficient 0.2%. I mean, for manufacturers, that massive reduction is a total game changer. It means lighter products, vastly lowered material costs, and way less chemical filler diluting the pure strength of the plastic. So the really crucial point here is that material engineers are constantly making strategic choices, and oceanchem provides a dual-track approach to support that balancing act. On one hand, you've got highly economical, battle-tested brominated classics like TBBA. These are absolutely fantastic for keeping costs low in mass global manufacturing.
But then, on the other side of the strategic coin, for markets demanding strict compliance with all this evolving green legislation, you have the next generation of eco-friendly halogen-free options like BDP. It's kind of like a constant dance between global economics, product performance, and of course, environmental responsibility.
All right, Section 3, securing foams and flexible resins. Because soft plastics definitely come with some hard challenges. You can't exactly make a mattress rigid.
Let's slow down for a second and consider the real-world stakes of these flexible applications. Think about EPS and XPS foams. These are used heavily in the insulation, hidden right inside the walls of our homes. If that catches fire, the entire house goes up. Here, FR130X serves as a vital economical alternative to phase out older, less eco-friendly chemicals. Then we have flexible polyurethane, which is the plush stuff inside your everyday mattresses and sofas. TDCPP is the invisible hero here, passing incredibly stringent furniture flammability tests so we can all sleep safely without worrying about a stray spark. And for flexible PVC, the chemical zinc borate really goes above and beyond. It doesn't just stop the flame, it actively suppresses smoke, because, as we know, smoke inhalation is often way more deadly than the actual flames. Zinc borate is literally a lifesaver.
That brings us to Section 4, Next-Gen Synergist and Innovations. Let's look at how we're completely re-engineering fire resistance.
Okay, get ready, because we need to talk about TR580FR. This is a totally fascinating chemical breakthrough for 2026. Earlier, we briefly mentioned antimony trioxide, or ATO, being used as a helper or synergist alongside the main flame retardants. But the thing is, ATO can be heavy, costly, and it definitely raises some environmental concerns because of its metallic nature. Well, TR580FR is a total game changer because it allows manufacturers to replace 100% of that ATO. And the mechanics of how it works are just incredible. When it's exposed to high heat, TR580FR's unique structure actively forces the plastic to form a really dense, strong carbon char layer. Think of it kind of like the plastic rapidly forming its own impenetrable fireproof scab. It traps combustible gases inside, it inhibits toxic smoke, and it completely stops those dangerous V2 flaming drips from ever even forming. Plus, it does all this at a highly efficient dosage of only 1 to 6%.
Finally, Section 5, the oceanchem production hub. We're grounding all this abstract chemistry right into manufacturing reality.
Because, let's be real, to supply these incredibly precise, complex formulations to the entire world, you need massive, highly specialized infrastructure. Looking at the immense footprint of the oceanchem facility, you can clearly see the staggering scale required to actually pull this off. We're talking about the crazy logistics of moving from a micro-level laboratory dosage of 0.2% all the way up to macro-level, thousands of tons global distribution. From the dedicated storage warehouses to the advanced R&D centers, literally every inch of this place is specialized. And most importantly, notice the vital on-site sewage and environmental treatment facilities. That is the physical proof of their commitment to the sustainable green manufacturing we were talking about earlier with those halogen-free alternatives.
As we start wrapping up this explainer, I really want to leave you with a challenge. The next time you plug in your phone, turn the key in your car, or just sit down on your couch, ask yourself, what is the invisible chemistry protecting me right now? And if you're a manufacturer tuning in, are your current formulations truly optimized for maximum safety, minimal costs, and the really strict environmental standards of tomorrow?
We've spent the last few minutes exploring exactly how we engineer modern materials to fight fire at a molecular level. But as our technology rapidly evolves and our safety standards climb ever higher, the ultimate question really remains: what will the chemical armor of 2030 look like? To make sure you're matching the absolute best protective armor to your product today, connect with oceanchem's 2026 Zero Carbon Aligned team. The science of fire safety literally never stops advancing, and making the right chemical match can quite simply save lives. Thanks so much for joining me on this explainer, and I'll catch you on the next one.